All right, we're starting with our next section, next topic, next unit actually, chapter 10, which is a unit on probability, and it'll lead into chapter 11 with statistics. So we're going to talk about a couple of problems that you'll see in sections 10.1 and 10.2. Okay, for the first three, it wants us to determine the possible outcomes in the sample space, which means all the possible things that can occur. So for the first one, you press a button on a computer program, when a button is pressed rather, a computer program outputs a random even number greater than 0 and less than 10. Okay, so we're going to do, for a couple of these, we're going to show you how would we determine what all the outcomes are, and then we'll talk about how do you not have to do that to compute the actual solution. So the numbers, even numbers greater than 0, less than 10 are 2, 4, 6, and 8. Okay, and you're going to do this 4 times. So here's kind of what can happen. The first time you could get a 2, and then the second time you could get a 2, a 4, a 6, or an 8. Or the first time you could get a 4, and the second time you could get a 2, a 4, a 6, or an 8. You could get a 6 the first time, and then a 2, a 4, a 6, or an 8. Or you could get an 8 and then get a 2, a 4, a 6, or an 8. So notice the first time we do this, our options are there's 4 options, 4 possible outcomes. The second time, there's 4, 8, 12, 16. So notice we take the first number 4, and we can have 4 more for each of those. 4 times 4 is 16. Well, if we do this a third time, you would do this all across the bottom, and you would get 16 times 4, which is 64. If you did it a fourth time, 64 times 4, which is 256. So it's taking 4 options times the 4 options, and you're doing that 4 times 4 to the 4th, 256. We certainly don't want to list all 256 options. So here for our next situation, we have a chess club deciding when to meet for practice, trying to figure out all the possible times, days, classroom scenarios. So we start off with practice days are Tuesday, Wednesday, or Thursday. So you have a Tuesday, a Wednesday, or a Thursday. So there's 3. Now we have possible times of 3, 4, or 5 o'clock. So for Tuesday, we could have 3, 4, or 5. For Wednesday, 3, 4, or 5. Thursday, 3, 4, or 5. So notice 3 options for days, 3 options for times, 3 times 3, now we're up to 9. And then the last thing is there's 10 classrooms. So again, we don't want to do this for all of them, but for this, we could have classroom 1, 2, 3, all the way up to 10. And then you'd have 10 options on this branch, 10 here, here, all the way across. And so 3 times 9, or 3 times 3 rather, and then you'd have 90 options here total, right? So in essence, we can take our 3 options for days times our 3 options for times the 10 options for classrooms, and we get 90 as our possible number of outcomes. And so just jumping to that idea here, jewelry store sells gold and platinum rings, so there's 2 options. Each ring has 7 styles, so 2 times 7. Each one fitted with 6 gemstones times 6. 2 times 7 times 6 is 84, and so there are 84 possible outcomes in that sample space. All right, moving along to some independent and dependent events. So the question for these 4 are the events A and B independent or dependent? So if they're independent of each other, then the probability of A and B occurring is equal to the probability of A times the probability of B. So in other words, once you do A, that has no effect on whether B occurs or not. And so here we're given that the probability of A and B is 21 over 200. The probability of A is 3 over 10. The probability of B is 3 over 10. That's 9 over 100. That is not equal to 21 over 200. So in that scenario, we would say these obviously are not independent events. They are dependent events. So somewhere along the line, they're dependent on each other, and we'll see some scenarios here with what that means. So doing that same thing here, we would have 3 over 10. If these are independent, would equal the probability of A times the probability of B. So this gives us 6 over 20, which does reduce to 3 over 10. So that tells us these events are independent. Okay, so now here's one of our conditional probabilities. And so if these again are independent, then the fact that B has occurred plays no role in whether A occurs or vice versa. So the probability of A and B is 2/5 times 1/5, or 2 over 25. Well, if these events A and B are truly independent, then this would be equal to the probability of B times the probability of A occurring given that B's occurred. Well, that would be 1/5 times 2/5, which is 2 over 25. Those are in fact equal. So these events are independent of each other. And again, it'll make a little bit more sense maybe down here when we do some examples. Here, the probability of A and B occurring, 3 over 10 times 1/2, which is 3 over 20. If these are truly independent, then the probability of B occurring times the probability of A given that B's occurred. In other words, the probability of A occurring doesn't matter whether B's occurred or not. These would be equal, and we would have 1/2 times 27 over 100, because there's our conditional. And this is 27 over 200, not equal to that. So somewhere along the line, these events are dependent on each other. Okay, so what does that mean in terms of a scenario? So here we have a bag containing 4 red marbles, 7 blue marbles. We randomly pick a marble and then pick a second marble without returning the marbles to the bag. What's the probability, and both marbles are red, that's where the probability is. Well, it doesn't ask us to find the probability, but we'll do it and we'll show you. So if we have 4 red and 7 blue, that's a total of 11. We're going to randomly pick a marble and we want both marbles to be red. Well, if the first time we do it, we have 4 red marbles divided by 11. Well, if these events were truly independent, then the second event wouldn't matter whether the first one occurred or not. But the problem here is we do not return the marble. So the second time we do this, we've already removed a red marble. So now there's only 3 to choose from, and now there's only 10. So this probability would be 12 over 110, and this can reduce to 6 over 55. But notice the idea that this probability changes because of what happened. So these are dependent events. This probability is dependent upon that because we didn't return the marble. Here we flip a coin and roll a fair 6-sided die. The coin lands heads up. Well, that's 1/2. The die shows a 2, that's 1/6. That would be 1/12. Well, after flipping the coin, then rolling a die, what happens with the die has nothing to do with whether the coin was heads or tails. So that would mean that these were independent, and I didn't write that these were dependent. Okay, so we'll see that again here. There are 14 shirts in your closet, 6 blue and 8 green. You randomly select one to wear on Monday and then a different one on Tuesday. And what's the probability you wear blue both days? Well, there are 6 blue, 8 green. So on Monday, the probability is 6 out of 14, but we're wearing a different one. So that means that this first one is no longer an option. So now we only have 5 blue to choose from and 13 total shirts, because we don't have the 14th because it has to be different. So the one that we chose on Monday is no longer an option. So now we would probably reduce this. This is 3 over 7, and so we get 15 over 91 as our probability. And again, this would be dependent. Here, 7 nickels and 5 dimes. I randomly pick a coin out of our pocket, return it, and then randomly pick another coin. Okay, so because we're returning the item, these will be independent events. The probability that the first coin is a nickel, well, there's 7 nickels divided by 12 total coins times. Now, the second time we want to pick a dime. There are 5 dimes. Now, because we've returned the coin, the previous coin that we've picked, we still have 12 coins to pick from. So what happened the first time has no role in what happens the second time, because it's the exact same option. So we have 35 over 144, and that would be that probability. So I hope this helps. There's some good problems from 10.1 and 10.2, and we'll see you soon.